everyone. We have to present our optimal cohort partitions, which is joint works of these units as routine situation. So what is the optimal cohort partition problem? So it's a problem where a planner wants to distribute a population of heterogeneous individuals into a fixed number of groups to optimize their objective. And this problem can have applications in many areas, from assigning students to classes, to forming teams of experts, to designing concepts among teams, to maximizing biodiversity. And in the paper, we see many of these applications. But the main focus of this paper is on education, and specifically on the optimal partition of students into classes in the previous year. So there is a long literature in the economics of education, dealing with the empirical identification of variables. And this literature is mostly 100% empirical, with very few modeling exceptions, which we will talk about. And has paid very little attention to the foundations of these models and the policy implications of different optimal partition plans. That said, few papers have theorized this idea that maybe we can sort individuals into groups to maximize efficiency. So one of these papers is this economics paper by Carl, Sackerdot, and West 10 years ago. So Carl and his team went to the US Air Force Academy. The US Air Force Academy uses what we call a uniform policy for their students. So basically, freshmen are randomly split into squadrons. But USFA and Carl wanted to change this policy with the goal of improving the performance of the students in the bottom one third of the distribution without harming the other students as much as possible. So to do that, they proposed what we call a nested policy. So basically, they put together the low-performing students with the high-performing students in some squadrons, and they put the remaining middle-performing students in separate squadrons. And what I find fascinating about this paper is basically that it had several unexpected results. So the experiment showed a negative and significant treatment effect for the low-performing students. And we don't really know what happened. They have several explanations. They say maybe middle-performing students are something like a social glue for the class. But our theoretical results indicate that perhaps the partition policy was suboptimal. So optimization so academics care about this problem, but policymakers also care about this problem. So here I have an example from a recent policy debate in Greece. So to give you some background, in Greece, students are mostly attending public high schools and are assigned to the school in the residential zone. So let's say we have like 100 students, like the first grade of high school. So the students need to be split into sections or classes of around 25 students each. And this assignment is done quasi-randomly, so basically alphabetically. But 2 years ago, the ministry wanted to change that for many reasons, but basically to improve the performance of the students, and wanted to do something that resembles tracking here in the US. In the US, at the same time, we see the opposite trend. So we see several states like California, like going from tracking to detracking, or what we call it uniform. So basically, the main debate here is performance versus inequality. Right? You might want the uniform partition or detracking to minimize inequality, or we might want the authority partition or tracking to optimize performance. So with this motivation in mind, we make two contributions to this paper. First, we offer a conceptual optimization framework for this general partition problem. We gain tractability through two ways. First, by using the length modernization theory, and second, by observing that several common objectives policymakers can take a convenient partition form. So we apply this to several applications like student assignment, information on this design, but we basically focus on education. So for education, we have several new theoretical guarantees and insights for common partition policies, use of schools. Again, making a theoretical contribution to this chiefly empirical literature. So we have several policy takeaways. We will see, for example, we saw that as a planner's priority, gradually switch from the highest performing class to the lowest achieving class, then the performance of small partition will become progressively less assortative. So we move from gradually from the assortative partition to the fully uniform partition. Within the same behavioral model, so the several models, we see that trade-offs might not arise across different objectives. So we might achieve the optimal thing with the same goals. And finally, perhaps counterintuitively, we find that the uniform partition minimizes inequality across classes, but inequality within a class still persists. So here's the roadmap. I'll talk about the model in preliminaries, then show you the optimization framework, and talk about our education, and then very briefly mention the simulation with our data and other applications. Okay, so here's the formal definition of the problem. So we have a planner who wants to partition a cohort of n students into k classes. Each class has size n. And each student comes with an attribute xi. This could be their prior performance. If we're talking about partitioning high school students, this would be their final GPA at the end of the middle school. And we look at two kinds of partitions. We look at integral partitions. So mathematically, this is a finite collection of sets, pi I to pi k, that are pairwise disjoint non-empty sets with a union, whose union is the cohort of the students. So each set corresponds to a class. So if I have, let's say, 6 students here, and I have 2 classes, one integral partition would be like this. And for this integral partition, we use the notion of summation vector. So this is simply the sum of the different attributes of this class. So for the first class here, I just like sum x2, x3, and x4. We also define fractional partition, so this is a little bit more general. So let's say we could split, the student like into different classes. Here's just like 1/2 for everyone. This would be a feasible fractional relation. Again, we define summation vector. This seems like more complicated, but I will show you like no weird fractional partitions actually come up as well. So what type of partition policies may be optimal? Here are some like definitions of like the different partitions that we find. With the sorted partition, I just like sort students based on performance and then assortatively assign them to classes. So the top students are in class 1, the next group of students are in class 2, and so on. Another integral partition that might be optimal is the next partition. This is similar to what Karel did. This is the formal mathematical definition, but to give you some intuition about that, imagine that we have sorted the students. This is like a necklace, right? Like this is one end, and this is the other end over there. And then it just like folded randomly at some point. So basically, I pair like the 2 ends of the students in one class, the second group of students in the middle here, and the middle performing students are in the last class. In terms of fractional partitions, as I said, like no weird partitions like come up as optimal. Uniform might be optimal. Uniform is a partition where each class is representative of the population, is proportional to the population characteristics. We also have like the 2 upper uniform class, which is a special case of a more general class we will see. How we construct this is just an intuitive description of the definition. Basically, we take the assorted partitions, and then we look at the 2 top classes, so the class of the top performing students, and then we uniformly shuffle around so that both classes are the same. Okay.
So one interpretation of the fractional matching partition could be they are assigned to different classes at different time. Or do you try to present
there are many interpretations? Yes, like this is more of a mathematical construction. But if we're talking about, for example, assignment of formation of teams, would be that I'm splitting my time as an employee, in one team and then like the other time in another team. In education, one interpretation could be that students may have a different grade, but are more or less similar. in terms of like categories, like the education literature often uses like high performing, mid performing, low performing students. So I might consider that, like similar, so like a fractional partition doesn't need to really like split like it's to students that are 18, I can consider them equivalent. So like going to the optimization framework, here's like the problem we are trying to solve. So the planner wants to choose a feasible fractional partition to maximize an objective. This could be like any objective f that is a function of the partition. We also look at this like special class of functions that are part additive. So they can be written as a small function f that is a function of the summation vector. So this is like we use for all fractional partition. So and here's like the main reduction idea. So basically we start from this like general problem, which is like computational very hard to solve. And we're looking for a feasible partition that maximizes function f. But we reduce it to a more practical problem by making two observations. So basically we observe that the original objective can be reduced to a part additive objective for the objectives that we care about as the policymakers. And also we can reduce the search space. So instead of looking for any feasible partition policy, we can search for an optimal solution over the space of the summation vectors of these policies that are majorized by the summation vector of their sorted partition. So what does it mean to majorize? So here's the technical definition. I will not go over it, but just like give you an example of something. So let's say we have sorted the summation vectors and X majorizes Y. So intuitively, this means that Y distributes like the students more evenly compared to X. So here's an example of what this means. Let's say I have this sorted partition. So like the top students are in the top class. The second students are like in the second class and so on. And I also have like another partition, like a nested partition, which is on average uniform. So you see there are different students like in the classes, but like on average it looks the same. So then this assorted X still the partition majorizes the nested one. And we can see this like graphically because this like next partition is like a not diagonal, like it's like uniform, but the L curve of the assorted partition like is above that, so it's more uneven compared to the nested partition. So it turns out if we take all the summation vectors that are majorized with this assortative partition summation vector, we can find a polytope. And even further, we can find an equivalence between this majorization polytope and the space of all the feasible fractional partitions. So we show this equivalence, basically say that if you have like any feasible partition, then the summation vector will belong to the polytope. But if we also take like any point here in the polytope, then we can find a feasible partition. And this already tells us like a lot of things like for the optimal partition. So we can immediately say that if this objective is sure-convex, then the assorted partition will be optimal. If it's sure-concave, then the uniform partition will be optimal. But of course, like this is not all the objectives we can have. What if, neither holds? So in this case, we show that like a class of equal locally uniform partitions is optimal. This is similar to the notion of the two upper uniform partitions that I showed you earlier. So the idea again here is that we sort all students. I just start with the assorted partition and then define blocks of consecutive classes. But within each block, I'm going to shuffle students around so like the classes will settle. And it turns out that if our objective is quasi-convex over this polytope, then this local uniform partition will be optimal. Actually, this is like a weaker statement than what we can prove. Like based on this standardization by Huang and Rosenblum, like we can use like a weaker norm of convexity called the like quasi-convexity. So it is even kind of straight and further. Okay, so what does this mean for education? We apply this framework now to a problem where we partition students into class under their effects. And for that, we need a model of how to model students' behavior. We use the workhorse empirical model from the literature and education, which is called linear in means. So the general idea in all this model is that each student puts some effort in class. This is reflected in her final GPA, so that's how we can measure it. And this effort is a function of their own characteristics, both observable and unobservable, but also the effort of their classmates. So the linear in means model says that everything is linear, and that the effort linearly depends on the mean action of its peers. And there were no theoretical micro foundations for this until very recently, and this like econometric paper by Cohort and authors, they offer two different micro foundations. The first one is the spillover model, where they model the utility of the student by using some multiplicative factor for the peer group pressure. But they also use the conformist model where we have a quadratic factor for to represent the price for non-conforming to the peer's behavior. In both cases, we can see that the first order condition gives us the linear in means model from the empirical literature, and we can also find the uniqueness. So for these two models, we look at several objectives. So we start with the performance, which is measured by the total weighted effort. And the main takeaway is that basically as the planner's priority gradually shifts from the highest to the lowest achieving class. So if my weight is, like higher, the highest for the highest achieving class, then I might have the sortative partition, but I will have the sortative partition as optimal. But as I move to the lowest achieving class, I care more about the lowest achieving class, I gradually move from assortative to the two upper uniform to uniform. So gradually to less assortative classes. For welfare, we find that the optimal partition depends on the actual macro foundational model. So for the spillover model, the assortative is optimal. For the conformist model, and for most reasonable cases, including what parameters we have in our data, the uniform partition is optimal, so we see discrepancy here. For diversity and inequality, we show again that the uniform partition is optimal. Two quick observations. Trade-offs, as I said, might not always arise, so depending on what model we have and what are the priorities of the planner, maybe the uniform is optimal for all different objectives. And also, the uniform partition is indeed optimal, but doesn't achieve a zero Gini index, so like not zero inequality. And to see that, since I don't have like a lot of time, I'll just like quickly, I won't go over the data. We have data from about like 10% of public high schools. We run some simulation with this data, and here's how the inequality shows up. So we have sorted students here by started performance, and we look at the effort level for different partitions by varying the effect of peer effects. You see that depending on the partition, like the highest performing students might have like very different gains from the lower performing students, even if they're in the same class, depending on the partition. And I wrap up with like briefly mentioning the other applications we have in the paper. So we look also at the nonlinear effects model that was recently proposed, the optimal assignment of experts to teams, and also a different model that has been used to model peer effects based on total competitions. And I'll stop here. Thank you.
Why the method assortative factor is a listed model because it's never already.
So theoretically, it depends on the optimization objective. So looking at their econometric paper, they don't have like the exact optimization formulation they use, but like we try to guess what they could have used like as their optimization objective. They had a numeric solution to propose like their next policy. And with the two objectives that we worked with, we showed that either the uniform partition would be optimal in their case, or a different type of nested partition of the continuous.